In this video, we are going to build a mechanical assembly in SimMechanics. Specifically, we will talk about how to implement coordinate transforms, represent degrees of freedom, and specify body interfaces for reusability. We will continue to build on our suspension system example. Recall that in the building components training video, we modeled the components of a suspension system that consists of a simplified chassis, suspension arm, and a tire with a rim to form the wheel system. Let's switch to MATLAB to see what this looked like. Let's open the model suspension assembly start. Here we see all the components that we created in the building components training video. Let's update this model using the shortcut Ctrl D to bring up the Mechanics Explorer. Let's switch to the Isometric View. We saw that all the components are aligned along their center of mass. We also saw that when we simulated this model, we couldn't see any dynamics. We will position the components and specify degrees of freedom for this model in this video. To position the components, we will be using rigid transform blocks. We have already introduced them in the Introduction to Multibody Simulation training video. Let's take a look at this in detail by switching back to our presentation. The rigid transform block allows us to reorient bodies. This block defines fixed relationship between base B and follower F coordinate frames. This relationship is defined by translational and rotational transformations. We can specify the following methods of translation: standard axis and elementary translation along one base axis, Cartesian three-dimensional translation as a vector x, y, z, cylindrical three-dimensional translation as a vector r, theta, and z. Similarly, there are several ways to do rotational transformations as well. Rotation along a standard axis is defined with the right-hand rule. The axis of rotation is defined positive in the direction of the thumb. The tips of the other fingers point to the direction of the rotation. Please refer to the documentation link in the resources section to get more information about this. We can specify the following methods of rotation: standard axis, where the elementary rotation is along one base axis; arbitrary axis, where the elementary rotation is along one custom axis expressed as the vector x, y, z; aligned axis, where we have two axis mappings between base and follower coordinate frames; rotation matrix, where we define a 3x3 rotation matrix from a base to a follower frame; rotation sequence, where we specify frame rotation as a sequence of three elementary rotation angles and axes. Let's use these translational and rotational transformations to position our suspension components appropriately. Let's go back to MATLAB. In our model, let's open up our Mechanics Explorer. When the mechanical system has several components, there might be a necessity to hide certain components while show certain other components to be able to work incrementally on the model. In our model here, let's hide all the components except the simplified chassis and the arm. To do this, let's right-click on the chassis simplified and say Show Only This to show only the chassis. Now right-click on the arm and say Show This. This way, we can use selective visualization to debug, build, and analyze our model. Now, let's position the arm using translation and rotational transformation that we just discussed. For this, let's use a rigid transform block. Open up the Simulink library browser. Scroll down to Simscape and open up the SimMechanics second generation library. Find the frames and transforms library to find the rigid transform block here. Let's add this to the model by right-clicking on this block and say Add Block to Model. Now we see the rigid transform block. This block is going to define the relationship between the chassis and the arm. So let's name it appropriately. So in this case, let's call this chassis to arm. Let's bring our model to the left here. Double-click the block to access its parameters. As we discussed in the Introduction to Multibody Simulation video, we can specify both translational and rotational transforms using this block. First, let's specify the translation. With respect to the chassis, we need to move the arm along the y-axis by half of the chassis width. We can see that by switching to the right view, and here is half of the chassis width. Let's go back to the isometric view. We also need to use the Arm1 chassis distance parameter to move it to the appropriate position in the vertical z-axis. So in the right view, this position is here. Let's go back to the isometric view. To do this, let's access the translational component. For method, we will use the Cartesian method to specify the translation in two axes. So here we can say along the y-axis, this is chassis width over 2. And the z-axis, which is the vertical axis, we use the parameter arm1 underscore chassis distance. Let's set the units to centimeters. Let's select OK to save changes. Let's connect the rigid transform block between the chassis and the arm. In our Mechanics Explorer, we can update this diagram by clicking on this button to see the arm move. So in our right view, we can see that the arm has moved by half of the chassis width in the y-axis and by the distance arm1 chassis distance parameter in the z-axis. Let's go back to the isometric view. Notice that we still need to rotate the arm about its z-axis by 90 degrees and the x-axis by 90 degrees as well. Note also that this is with respect to the arm. At this point, it is good to start thinking about interfaces between bodies. For example, what is the link between the chassis and the arm? We will talk about this when we are implementing joints later in this video. For now, let's assume that there is a connection here that is going to model the connection between the chassis and the arm. The rotations of the arm are with respect to the reference frame of the arm. So let's add another rigid transform block. So let's go back to the Simulink library browser, right click on the block and add it to the model. So we have the rigid transform block here. Let's rename this to be between arm to chassis. Since this rigid transform block is going to be with respect to the arm to the chassis, let's flip this block using the shortcut Ctrl-I. Let's connect this block between the arm and the chassis here. Double-click the block to access its parameters. Recall that we need to rotate our arm about the z and x-axis by 90 degrees. Let's do the rotation about the z-axis first. We can choose the z-axis here and say rotate it by 90 degrees. Select Apply and update our diagram. We see the rotation. We can also see that we need one more rotation about the x-axis to complete the orientation. We can add another rigid transform block and do another rotation about a single axis, which is the x-axis. However, to reduce model clutter, it is recommended to do multiple rotations using the aligned axis, the rotation sequence, or the rotation matrix method. Let's switch back to the original configuration by setting this to no rotation, apply, and then update the diagram to go back to the original configuration. For our example, to do multiple rotations, we will use the aligned axis method. Here is the reference frame for the arm. When we rotate this about the z-axis by 90 degrees and the x-axis by 90 degrees, the resulting frame looks like this. The original reference frame is the base frame. The resulting frame is the follower frame. So when we align these axes, the base z becomes the follower x, and the base x becomes the follower y. Let's apply these changes to the transformation and then update our diagram to take a look at our arm. Now we see that the arm is in the correct orientation. Let's switch to the right view here. We can verify the orientation of the arm in this view. Notice also that we still need to do another translation by half the length of the arm to position the link on the chassis. We can do this in the same block here. So we can say translation about a standard axis. So in this case, about the x-axis of the arm, and we will translate it by arm1 underscore length over 2. Let's set the units to centimeters. Select apply and then update our model. We see that our arm moved to the left. However, we want the arm to move to the right. So let's negate this offset by providing a negative sign here, apply, and then update our diagram and fit this model to view to see the chassis arm connection at the right position now. This is a good example that shows how we can use rigid transform blocks and model update function to position our components appropriately. Next, we need to take care of the connection between the arm and the rim. To do this, let's show the rim solid by right-clicking on this component and say show this to bring up the rim solid as well. Let's switch back to the isometric view. There are two operations to do to orient the rim correctly. First, we need to translate the rim to the end of the arm. Next, we need to rotate the rim to position it perpendicular to the arm. This rotation is going to be with respect to the rim about its y-axis. Go back to our library browser and add another rigid transform block to our model. Let's rename this arm to rim. Let's connect this between the arm and the rim. This is going to be the translation with respect to the arm. Double-click the block to access its parameters. This is the translation only operation about a single axis, so we will use the standard axis format. And about the x-axis of the arm, so here we can see the arm's x-axis is along its length. We will move the frame by arm1 underscore length over 2 and set this to centimeters. Select apply, and now when we update our diagram, we can see that the rim moves to the end of the arm. We can switch to the right view and take a look at the rim coordinate system to see that it is at the end of the arm. Let's go back to the isometric view. Next, we need to rotate the rim with respect to the y-axis of the rim by 90 degrees. So let's select OK to save changes here. This rotation is going to be with respect to the rim component. So we can imagine another link between the arm and the rim here that we will model later using joint blocks. So let's go back to our Simulink library browser, add another rigid transform block to our model. And this is going to be from the rim to the arm. Let's also flip this block using our shortcut Control I because the transformation is going to be from the rim to the arm. Let's connect this between the rim and the arm. Double-click the block to access its parameters. The rim's rotation is going to be about its y-axis by 90 degrees. So we can just choose the standard axis method to rotate it about a single axis. In this case, that is the y-axis, about 90 degrees. Select apply and then update our diagram to take a look at the rim. Although the orientation of the rim seems to be correct, the arm rim connection is at the center of the rim. Instead, it needs to be translated about the vertical axis by the wheel bias 1 parameter. In this case, the vertical axis is the y-axis, so let's use the same block to do the translation about the standard axis, in this case the y-axis, and move it down by the wheel bias 1 parameter. Select the centimeters as unit, apply, and then update our diagram to see the rim move down and the arm is connected to the upper part of the rim. So now we have positioned the arm with respect to the chassis and the rim with respect to the arm. Let's show all the solids in our model by right-clicking on any of the solid blocks and say Show Everything. We can see that the tire is also positioned correctly. This is because the tire is directly connected to the rim, and any transformation that the rim undergoes, the tire also undergoes. Now that we have the correct configuration, let's simulate this model by clicking on the Run button here. We still don't see any dynamics in the model. This is because even though all the components are positioned correctly, they are still rigidly attached to each other, and we need to define degrees of freedom for the components with respect to each other. To do this, we will use the joints library in SimMechanics. Let's go ahead and access the joints library. So go to the Simulink library browser. We can see the joints library here. We see several joint blocks. For example, we can see the prismatic joint, the planar joint, the revolute joint, etc. For our example, we will model the link between the chassis and the arm here, and the arm and the rim here using a revolute joint. Let's take a look at these positions in the right view. So the joint locations will be here. Let's go back to our isometric view. We talked about joint blocks and the revolute joint in our Introduction to Multibody simulation video when we modeled the single link pendulum. Let's add this block to our model. Let's go back to our model here. So the connection between the chassis and the arm will be a revolute joint. Recall that a revolute joint has a single degree of freedom which lets the bodies rotate about the z-axis. So it is important that the base and the follower z-axis align. In our case, we would like to connect the joint between these two rigid transforms. So the base in this case will be the follower of the chassis to arm transform. We can take a look at it here. We see that the z-axis is pointing upward. However, for the revolute joint to make sense, it needs to be pointing out of the screen. Let's take a look at the arm to chassis transform and its follower. We see that it's at the same position at the same orientation. So this z-axis also needs to be rotated to be pointing out of the screen. So in this case, even if our base and the follower frames are co-located, in other words, the origins are at the same position, they are not oriented correctly. We need to align these z-axis to be pointing outward of the screen. To do this, we will do additional rotations in our rigid transforms, which is the chassis to arm and the arm to chassis. So let's double click on the chassis to arm transform. We see that currently doesn't have any rotation. Let's take a look at the follower of the chassis to arm. To point the z-axis out of the screen, we need to rotate the frame about the y-axis. So let's say about a standard axis, in this case the y-axis, rotated by 90 degrees. We can select OK and then update our diagram. We see that our z-axis is pointing outward. However, the configuration of our model has changed. Notice that the arm is oriented incorrectly. It also seems to be connected to the lower part of the rim. This is because we still need to correct the follower frame for the arm to chassis frame here. To do this, double click on the arm to chassis transform. We already have an aligned axis format here. We will change the new follower negative x to be plus y and the new follower positive y to be plus x. Select OK to save changes and update our model. So now we see that the z-axis is pointing outward for the arm to chassis transform and the chassis to arm transform. We also see that by correcting the z-axis alignment, we are back to the original configuration where the arm is oriented correctly and is connected to the upper part of the rim. Now that the z-axis are aligned and oriented correctly, let's connect the Revolute joint between these two transforms. Update our model. We can see the Revolute joint here. We can also see the z-axis is pointing outward, which is the correct orientation. Now let's simulate the model by clicking on the Run button. We see the revolution about the Revolute joint. We see that the system behaves like a pendulum with only forces under gravity. We also see that the wheel system is rigidly connected to the arm. Next, let's add a Revolute joint between the arm and the rim here. Before doing that, let's make sure that the z-axis are aligned and oriented correctly. So in our Mechanics Explorer, let's update our diagram to go back to our initial configuration. And in our arm to rim transform, let's take a look at the follower. We see that the z-axis is pointing outward, which is the correct orientation for our Revolute joint. Let's take a look at the rim to arm transform and the follower. We see that it is located at the exact same position, which means the two frames are aligned for our Revolute joint. We also see that the z-axis is pointing outward, which is the correct orientation for our Revolute joint. So in this case, we don't need any additional rotations or transformations to make the z-axis point correctly for our Revolute joint. It is good practice to always think about how the joints will be aligned ahead of time so that we don't have to do corrective rotations later. So let's go ahead and delete our connection here and copy our Revolute joint by right-clicking and dragging on this block and connect it between the rim and the arm. Let's update our diagram. We see Revolute joint 1 here, which is the connection between the arm and the rim. We also see its location in the isometric view here and the right view here. Let's go back to the isometric view and simulate our model. We see that the system still behaves like a pendulum with only forces under gravity. We also see that the wheel system is moving with respect to the arm. This is the expected behavior. Let's update our diagram again to go back to our initial configuration and switch to the right view. Next, let's complete our model by creating a second arm and connecting it to the rim. Sim mechanics blocks can be grouped into subsystems that can have physical connections, physical signals, and Simulink signal ports. Grouping blocks into subsystems makes our model easier to read, navigate, and to reuse the components that we define. So in our model, let's group all the arm-related components. So in this case, it will be the two transforms and the arm solid block here. And let's use the pop-up menu to create the subsystem by clicking on this option. So we see the subsystem here. Let's rename the subsystem to be Arm Subsystem. Double-click on this block to access its contents. We see the physical connection port interfaces to the rest of the model. Let's rename this to be the chassis connection and this to be the wheel connection. Let's go back to the top level of the model to see that the chassis and the wheel connections are reflected. Similarly, we can group the wheel-related components and the chassis-related components to make subsystems out of them. So let's go ahead and do that. Now, to create the second arm, the lower arm, let's copy the arm subsystem by right-clicking on this arm subsystem and then dragging to create a copy. Let's rename these subsystems. So this one is going to be called Arm1 subsystem, and this one is going to be called Arm2 subsystem. Double-click on the Arm2 subsystem to access its contents. Now we need to specify the Arm2 parameters for all the blocks that we have under the subsystem. Note that this can be simplified by masking the subsystem. Please refer to the documentation link in the resources section regarding masking to get more information about this. For now, let's manually change the parameters to reflect the Arm2 parameters. So here in the translation, we have a reference to Arm1. So let's change that to Arm2. Same goes for the other transformation here. Let's also change this under the solid block. So in the function that we call here, let's change it to the Arm2 parameters. Select OK to save changes. Let's go back to the top level of the model. Next, let's create the interface from the chassis to Arm2. To do this, let's double-click on the chassis subsystem to access its contents. Let's rename the existing connections to Arm1. Let's copy these two blocks by selecting these blocks and right-clicking and dragging on these blocks to get the Arm2 connections and connect it to the chassis here. Double-click on the chassis to Arm2 transform. Here we will specify the Arm2 chassis distance parameter. Select OK to save changes. Also double-click on the Arm2 connection port to make sure it lines up on the right-hand side of the parent subsystem. Select OK to save changes. And go back to the top level of the model to see that the Arm2 appears on the right-hand side of the subsystem. Recall that the connection port blocks used to define the subsystems can be found in the Simscape library. We have already talked about this in the Simscape training video. Now, let's connect the chassis subsystem to the Arm2 subsystem. Let's copy a Revolute Joint as the link between the chassis and the Arm2 subsystem, and connect the chassis to the Revolute Joint and the Revolute Joint to the Arm2 subsystem here. Next, we need to create the interface between the Arm2 subsystem and the wheel. So double-click on the wheel subsystem to access its contents. Let's rename the existing connections to Arm1. Copy these two blocks by right-clicking and dragging on these blocks to create the Arm2 connections. Connect this to the rim. Double-click on the transform to see if there are any references to Arm1. So here we have wheel bias 1. This needs to be wheel bias 2 for the lower arm. Select OK to save changes. Let's also double-click on Arm2 to make sure it lines up on the left-hand side of the wheel subsystem. Select OK to save changes, and go back to the top level of the subsystem to see the Arm2 connection port here on the left-hand side. Let's copy the Revolute Joint to model the link between the Arm2 subsystem and the wheel subsystem. Connect the Arm2 subsystem to the Revolute Joint and the Revolute Joint to the wheel. Let's bring our model to the left here and update our diagram to bring up the second arm, which is the lower arm. Let's switch to the isometric view to take a look at this connection. Let's simulate the model. We see that the system is not fully constrained since the two arms are not bounded by a shock absorber component of some kind. We will take a look at this in the next video, Building Mechanical Assemblies Part 2. In this video, we have positioned the components, implemented degrees of freedom, and visualized the simulation. We also discussed subsystems and how it will be useful to reuse components. Let's go back to the presentation and do a recap. We first positioned the arm. To do this, we translated the arm from the chassis first. Then we rotated and translated the arm itself. Attaching the rim required translation from the arm and rotation and translations from the rim itself. We did this to position the rim such that the upper arm is attached to the upper part of the rim defined by the wheel bias parameter. We then specified the degrees of freedom for our model using joint blocks. For our example, we used Revolute Joint blocks to provide a single rotational degree of freedom between the chassis and the arm and the rim. Next, we modularized our system by creating subsystems. We used connection ports as interface points for the subsystems. We then reused the arm subsystem and parameterized it for the lower arm appropriately. We also created interfaces in the existing model to connect this component. We then ran a simulation to see if we still need a component to act as a shock absorber and fully constrain the system. In summary, we talked about how to implement coordinate transforms using rigid transform blocks and represent degrees of freedom using joint blocks. Finally, we discussed how to specify body interfaces and reuse components using subsystems. This concludes this video.